Hi everyone. So today we're moving on from processors and obviously the virtualization of the CPU and onto memory, which is just another component of the system that gets virtualized by the operating system. And that's back to that same idea where the operating system generates or creates this abstraction, which abstracts the physical hardware, in this case our memory or RAM. So just to recap of last week, right, we touched on the interrupt stack and how different interrupts are processed in terms of system calls and upcalls and how they're actually implemented in a safe fashion. And by safe, it means that um, it's safe enough that it prevents against unauthorized access during the processing of both of these interrupts. And last part of that, we looked at Unix. And in the next lab you'll be playing around with some of those Unix commands that we touched on last week. So on to today's lecture, focusing mainly on memory virtualization. So what is memory virtualization? Well, like I said in the introduction, the operating system virtualizes its physical memory. And this goes back to that idea of the illusionist. And the OS provides an illusion of memory space per each process. So each process thinks it has its own memory space. And once again, to each process, it also seems that it has the entire memory for it to use, for itself to use. Now, what are the benefits of performing this memory virtualization? Well, there's the ease of programming, right? We just specify, in terms of when we write code and stuff like that, we just specify how much space we want. So if we're using malloc, we'll specify like the size, and we just define things. We don't say where they go or how they're stored, because all of that is abstracted away from us, right? The operating system handles that for us. And this allows for efficiency in memory in terms of time and space. And there's a guarantee of isolation. So this means that there is protection from errant access of other processes. So what this means is that other processes can't access your protected memory because they're isolated, they're separated from each other. Now, how did memory management work in early operating systems? Well, you would simply load one process into memory. That's all you could do. One process as well as the operating system. And this was obviously a form of obviously poor utilization and efficiency, right? You want to have multiple processes in memory so that they can be accessed quicker and they can be swapped in and swapped out of being executed a lot quicker as well. The key thing here is that physical hard storage, so like your ROM, is slower than RAM, right? So if you can only store one process in memory, you have to then save it into ROM or like hard disk and then load the other one in, right? And that takes a lot longer than if both of these processes were in memory already. So along came multi-programming and time sharing. This concept of time sharing we've been talking about quite a bit, where we have like a timer interrupt, which promotes or which forces a context switch between two processes. So yeah, this idea of multi-programming allowed us to load multiple processes into memory, and you would execute one for a short time, switch processes between, and increase utilization and efficiency. However, this caused a problem, right? And that this problem was related to protection. And if you have multiple processes in memory, well, what's stopping those processes from accessing other parts of the memory? So this was a big concern and a problem that had to be solved. And as a result of this, in order to solve this problem of protection, we needed a way to isolate processes in memory and only allow authorized access to memory addresses. And this is what the operating system does. And to do this, the operating system creates an abstraction of the physical memory called the address space. Now, the address space contains all the info about a running process, so everything that you would think was in memory is what's contained in the address space. So this is the program's code, the heap, stack, etc. Now, we touched on this a little bit, but just to remind you, the code is obviously our instructions, so those executable instructions, or this is where they are stored. The heap is where all dynamically allocated memory is stored, so whenever you use malloc or new. And the stack stores our return addresses or values and contains local variables arguments to routines. So what does this address space mean? Well, now each process is contained within its own address space. So each process is mapped to its own address space, and the address spaces the address space for each of these processes start at 0, while a process in physical memory, as you can see here, may not necessarily start at 0. So process A starts at 128 KB, whereas its address space starts at 0. And I'll get into what these numbers, how they translate exactly a little bit later. So just to clarify as well, that processes are still stored in physical memory, of course. That hasn't changed, right? But those physical addresses are now accessed via the address space. So the question is obviously, well, how do we map between our physical memory and the address space? And it's the operating system's job to facilitate this process. Now, every address in a running program is virtual. Now, this virtual address is the address that you would find in its address space. So whenever you see addresses that are being maybe displayed from a program or something like that, those are its virtual addresses. And it's the job of the operating system to translate this virtual address to the physical address so you can actually find where the data actually is stored, right? So here's an example of some code that displays addresses of different locations, namely the code, the heap, and the stack, right? So if you were to run this program, you'll see the virtual addresses. Now that's important. It's the virtual addresses and not the physical ones. And that is because the operating system is abstracting that away from us. We as a program or a process don't have direct access to that information. And that's because we want to enforce some sort of protection. So here's the hypothetical output of that code that I demonstrated. Now, this is just hypothetical, of course, and I encourage you to run that code at home and to see what values you get. But you would see here now, if this is our representative address space for that program, you can see that the heap is at this address, and that corresponds to here. The stack has this address, and that corresponds to here. And the code has this address, which corresponds to here. So that's basically what these values would be representing. So onto the translation, right? How we map, or how do we go from a virtual address to a physical address? Now, an actual hardware component handles this, right? It's not a separate process in the operating system that handles this. It's not like an interrupt handler for this. It is a hardware component that will handle this. So like a physical register that stores a value. Now, we obviously need these physical addresses, like I said before, because this is where the desired information is actually stored, okay? So the OS must get involved at key points to set up the hardware so the hardware can handle the address translation. The OS must manage its memory in order to judiciously intervene. Now, what does that mean? Well, it needs to intervene in terms of its memory management when maybe things have gotten a bit messy, and we'll be talking about this memory management component in the second half of this lecture video, so part 2, and that's more focusing on that aspect. So here's a little example of how address translation looks, or how it works. So here you'd have some code where we define an X variable and we simply add 3 to that value. And how this is basically you load a value, you increment it by 3, and then you store that value back. Now, obviously, all code gets transformed into assembly down the line when it needs to be executed, before it gets transformed into like our binary instructions. So this is currently what the assembly code for that previous piece of code would look like. So presumably that the address of X has been placed in register EBX, so this is just hypothetical. And you load the value at the address into the EAX register, so that's what this add all is talking about. Sorry, this is when you add in the 3, so that's this next line, add 3. And then you store the value back in memory. So this is just basic assembly code. You don't have to really know this exactly, but how it works on the next slide is important to understand. So that would be our program code, hypothetically, right? So this would be loaded or stored in the program code section. And these would be the hypothetical addresses where these lines would be stored. So once again, all I did was take that assembly code and plop it in here for just to represent what it would look like. So how it would be executed? Well, you would fetch instruction at address 128. And what is this? What is the instruction address 128? Well, it's this line here. You would then execute this instruction, and this instruction would say, because we're talking about this EAX register, load from address 61 KB. So that's this address over here in the stack, and it's going to load, say, this value. Okay. And then fetch instruction at address 132, and that is this instruction here. And then execute this instruction. It doesn't have any specific memory reference, so you just execute it. Then obviously you move down into the next instruction, which would be at address 135 hypothetically, and then you execute that, right? And just to note that this is in terms of the physical memory here. So hypothetically, if this was our entire physical memory, that's how it would look. But that's obviously not how it works, right? For our previous example on the last slide, since it starts at 0, it's easy to understand that the virtual address would simply just be the physical address, right? Because they both start at 0, they're both obviously the same size, so therefore they're equal. But it's not like that for every process. Now, what happens when the operating system needs to relocate a process, or another process is stored at an address that is not at the beginning, or the starting address is not 0, then what do we do in those cases? So a hypothetical scenario is kind of like this, right? Here we have process A starting at 128. Obviously its address space still starts at 0 and ends at 64. Just like process A will end at, has a size of 64 kilobytes. You can see that there. So what do we do in these cases, right? This is a lot harder. So it's a lot harder when we have these like relocated processes. And the question remains, well, how do we keep track of where all these different processes are in memory, and how do we map between these two spaces? And the solution to this is that hardware that I was alluding to before. And these are called our base and bounds registers. So our base register basically indicates the address, or points to the start of a process in physical memory. So processes A's base register is at 128. Okay? And we have the complementary register, the bounds register, which stores the last address, or basically the size of the process in address space. So this process starts at 0 and ends at 64, so the bounds register is 64. So we utilize both of these registers in order to do address translation. So how do we do the calculation? Well, when a program starts running, the operating system decides where in physical memory a process should be loaded. And when it does this, it sets the base register value to be that location. Okay, and now if we want to translate between virtual address to physical address, it's simply we take the virtual address and we add that base value, and this will give us our physical address in memory. Now there's some rules for addresses. Every virtual address must not be greater than the bound, and it can't be negative. So we have this little relation here, so it must be greater than or equal to 0, and it must be less than the bounds. If it fails on one of these conditions, then it must return an error, because in that case we're accessing memory that does not belong to us. Okay, so let's actually do an address translation. So let's convert a virtual address to a physical one. So in the previous example, I had this instruction. You can see here in the address space it's stored at 128. So the virtual address is 128. Okay, and we need to add the base value, right? Well, if we go back to the previous slide, well, a couple slides back, what was the base? It was 128, right? The beginning of process A. So that's why we say 128 here. So we say 128 plus 128 KB, because it's not simply 128, it's 128 kilobytes, and you'll get this value. Now 1 kilobyte is 1024 bytes, so you can do the maths there. 1024 times 128 plus 128 will give you this number. Okay, so let's do the second example. And this instruction is basically asking load from address 61 and load whatever value that was. So our address now, or our virtual address for this case, is 61 KB, and we load in, say, this 3000 value. So when we want to now translate this address from virtual to physical, once again it is our virtual address, which is 61, and that is the address inside the address space, which ranges once again from 0 to the max, to the size. And we then add that value to our base, just like we did in this one over here. So now it's 61 plus 128, which is the base, and that gives us 189. So that's how we handle our address translation. And just to answer a question probably before it comes up, do we leave it in bytes or do we leave it in kilobytes? Well, whenever I ask these types of questions, I will specify for you in which format do I want it. Do I want it kilobytes, megabytes even, or bytes? But yeah, the question will specify. Now, I've spoken about using this base and bounds register to indicate the beginning and end, essentially, of our process in memory. The base register being appointed to the start of a process in physical memory, and the bounds register being an indicator of the end of a process within address space, or the size of the address space. Now, there's actually two ways to implement this bounds register. One, like I've described already, where we point to the end of the address space, and another one where we actually point to the end of the process within physical memory, so as indicated by this bounds register over here. Now, both of them work and fulfill exactly the same role, and you can even calculate one from the other. So if you wanted to calculate like the physical bounds register, you could just take the physical base register here. You take the 128 value and you add it to the bounds register within the address space, and that would be 64. So 128 plus 64 giving you 192. And then in the same process, you could take this physical bound, or the pointer to the end of a process within physical memory, and take that value, so 192, and subtract it, and take 128 away from it, and then you could get 64. So the idea here is that you have one bounds register that represents the size of the address space, but you could in another way implement it where you have another bounds register which points to the end of a process within physical space. And they both perform exactly the same role and are utilized in the same, or at least in a similar way, to convert from virtual to physical address. Cool. So we know how to translate between virtual and physical. Now, what are some of the issues that an operating system must handle in order for this virtualization to be performed? So we discussed this first one. The OS must take actions to implement a base and bounds approach. So when they load a process for the first time into memory, they need to store its base and bounds. And then when that process is being executed, those base and bounds variables need to be loaded into the CPU. And what's cool is that we already have a component that we've discussed before which actually stores these variables, and that is our PCB. And you remember the PCB stores information relevant to individual processes? Well, this is just another component of that, right? Base and bounds is just more information to do with the process. And remember the PCB also stored the temporary states of the CPU when it was processing a process. Well, these base and bounds registers is just the components in the CPU, register in the CPU. So these would be loaded and stored in that same fashion within that saved state. Now there are three critical junctures when the operating system needs to step in order to handle memory virtualization. And that is when a process starts running, so finding space for our address space to fit in physical memory. When a process is terminated, so reclaiming the memory that was in use and making it now free. And when a context switch occurs, right? I talked about this already actually, but the saving and storing of those base and bounds pairs, right? When a process is loaded into the CPU, the base and bounds pairs must be loaded into their respective registers. And when it's taken out of the CPU or switched out, those base and bounds pairs needs to be saved again. So let's look at when a process starts running. So once again, we have a little diagram here of some physical memory, and I've overlaid our address space within a particular process here, so process A. So this is what it would look like. Now, the operating system must find room for this new address space to fit, right? If there's not enough space, it needs to make a plan and solve this problem. So in order to keep track of where there is free space, it implements a concept or a data structure called the free list. Now, this is a list of the range of physical memory which is not in use. So it looks kind of like this. It's an actual linked list that points to the start of locations that are free. So like 64 KB, so that's over here. So you can see this is the start of a free chunk. It also contains the size of a free chunk. I haven't indicated that here, but later on we're going to go into a lot more detail of this free list and you'll see it there. And then it will point to the next. So you guys are aware like a linked list has some value and then a pointer to another value or another node. So this will point to another data structure that stores information to do with the next free chunk. And that starts at location 320, which is wrong. This should be 256. Sorry for that mistake. Obviously that should be 256, the start at the next free chunk. And then that'll point to the last one here. And then this list will be changed obviously throughout the process of creating new processes, removing processes, etc. This needs to be updated. So what happens when a process is terminated? So here we have our hypothetical like physical memory with its hypothetical free list. So when a process is terminated, the OS must put the memory back on the free list. It must make that memory available again. So here, hypothetically, process C is concluded and terminated. So we need to adjust our free list in order to account for that change. So after the change, we now have a big chunk of free from 64 all the way to 320. okay, because 128 and 256, between 256 and 128 is now freed. And now our free list looks like this. So it pointed to 64 and then it pointed to 448. Okay, so that's how we handle when a process is terminated. And now the issue is when a context switch occurs. So here I spoke about already that the PCB is going to come into play. Well, the operating system must save and restore the base and bounds pair in the PCB of that particular process. So here we hypothetically have some physical memory where process B is running on the CPU. Its base register, or the base register within the CPU, has the value 320 and its bound register has the value 448. Then all of a sudden a context switch occurs for whatever reason, and it wants to switch between process B and process C. Well, these base and bounds registers are then stored in the PCB when that saved state is stored, right? It's part of the saved state, these variables. The process C is then swapped into the CPU, and when it is swapped into the CPU, its base and bounds registers that were within process C's PCB is loaded into the base register and the bounds register in the CPU for that particular process. So now those register values are 128 and 256, corresponding to the start and finish of process C. So that's what would happen for a context switch. Now, with this approach, right, what if there is not enough space together to fit a program? So we use these base and bounds to indicate basically the dimensions of a process. But what if there's not enough space to fit a program? What do we do then? How do we start a new program in this case? Well, this problem basically describes the inefficiency of the base and bounds approach. Now, if we have a big chunk of free space within a particular program, which you can allocate, this free space takes up a lot of space within physical memory. So remember, all of our processes are made up of program code, heap, stack, and free space, where during its processing it can store information as well as obviously remove information, because our heap needs to grow and our stack needs to grow. So now it is hard to run when the address space does not fit into physical memory. And because of this problem, a solution was made, and that was segmentation. Now, a segment is just a contiguous portion of the address space of a particular length. So instead of having a single process or an address space represented as a single object, it is now broken down into what we call segments. And you can make some logically different segments like the code, stack, and heap, like we've been talking about before. But now we can actually store each of these segments in a different place in physical memory, because there's not a necessity for these to be next to each other than through the ways in which we address them or reference them. So now if we're having all of these components or segments in different locations, we need a way of addressing each of those different locations. This means that we need to have a base and bounds pair for each segment. So here, in physical memory, we have this representation. So we still have like our stack, our code, and our heap, and their addresses are now correspondent to their individual base and bounds. I know it's called size, but this could be bounds. Their individual base and bounds pairs. So the code will have a pair, the heap will have a pair, and the stack will have a pair. And all of these pairs are stored in what is called the segment register. So it's just like if we just had two registers, one for the base, one for the bounds. Now this is a collection of registers that stores all of the segment information. And once we do context switches and stuff like that, all of this information is then stored in the PCB for like process A, process B, etc. Just like before. The only difference now is that we have a lot more registers, right? We have one for each segment instead of one for each or just one. Okay, so now there's a slight problem, because if we've changed the way in which we represent our memory, so now in terms of segments, our base and bounds registers represent different things now. So in order to properly reference instructions and data, we need to change the way in which we handle our address translation when we're working with segmentation. So now, instead of the physical address being the virtual address plus the base, the physical address is equal to an offset plus the base. Now, the offset of hypothetically virtual address 100 is 100, and on the next slide I'll explain how this works a bit better. And the reason for this is that, well, if virtual address is at 100 and the code segment starts at virtual address 0, well, then 0 plus 100 is obviously 100. Now, how does this translate into physical address? Well, we take that offset, which is 100, and we plus the base. And the base is once again stored in that segment register, and you can see it's 128. So this instruction will be represented somewhere here in memory at address 100 plus 128 KB. Okay, so this example might be a little confusing because it seems it's strange that 100 is 100, but this next one is a little bit better. But firstly, I just want to add here, the reason why we can't just say virtual address plus base is, well, will be demonstrated here. So the offset of virtual address 16,000 is 640. Okay, so how did I get that? Well, think about it, right? 15 KB, that means that it's 15 times 1024 bytes. So that gives you a value of 15,360, just off the top of my head. And we take 16,000 and we subtract that value, and that's how we get to 640. So what you're doing is you're taking the start of the segment and you're saying, okay, well, I have the virtual address minus the start of that segment. So we take 1600 minus 15 KB, and that's how you get the offset. So it's basically each segment now hypothetically starts from 0 and goes until its size, if you think about it in that sense. That's what the offset is representing. The offset is its position within that segment. So this instruction's position within that segment. And now if we want to convert this to a physical address, you would say offset plus base. So that's why you got 640 plus 192 KB. What happens if an address is incorrectly referenced? Well, you guys have probably all experienced this. Well, a segmentation fault occurs. Now, what leads up to segmentation faults? Well, if an illegal address such as 37 KB, which is beyond the end of the heap, heap ends at 30, if this value is referenced, the OS occurs a segmentation fault violation. And that's because the hardware, so our base and bounds registers, detects that this address is outside of the bounds and it flags an error. So how do we refer to segments so that we don't lead to these cases of segmentation faults, as well as how can we actually identify, or how is the identification of a segment fault actually done? So there's an explicit approach where you chop up the address space into segments based on the top few bits of a virtual address. So say this was a hypothetical virtual address represented in a register, so a binary value. Now you can chop up the first 2 bits, and we're going to call that the segment indicator, and the rest is going to be our offset. So if we had an example of a virtual address 4200, its binary representation, or its representation that it would have in an actual register, would look like this. And the first 2 bits we can use to specify what segments it's in. So this could be 0, 0, 0, 1, 1, 0, or 1, 1, right? Indicated here. Now, this allows us to generate value or indicate which segment it is based on the corresponding bits. So the code can be as a result of 0, 0, the heap 0, 1, the stack 1, 0, and anything else can be 1, 1. And our offset will just be the rest of the address. So what does this look like in practice? So here's some code that basically will indicate whether and convert between a virtual address and a physical address and indicate whether an exception should occur. So given this information, I have calculated the virtual address segment and offset, but we can go through it together. So the first thing says, well, let's get our segment. You remember our segment indicates what segment it's from, so it's those first 2 bits. And how to get this is, well, we basically take our virtual address and we AND it with the segmentation mask. I'll get to this in a bit. So we take our virtual address. So say this is our hypothetical virtual address. We then simply say an AND. So we apply the AND function onto with the segmentation mask. So how this works is wherever there's a 1, so this is a 0, that's a 1. This is a 1, that's a 1. Okay, so then the 1 stays, right? You're just applying the AND operation just like you did in VCO with AND, OR, NOR, etc. And the general idea here is, well, whenever there's both 1s, well, then there's a 1, everywhere else is 0. So that's how we get this segment value here. And then the rest of it is like these less than symbols and seg shift. And segmentation shift was basically this 12 value. And what it's doing here is saying it's applying a bit shift. Right? It's saying take this value and shift it to the right 12 bits. So you'll shift the 0, 1, well, you'll shift all of these values to the right 12 times. And the preceding values would just become zeros. So this would essentially be 0, 0, 0, 0, 0, 0, all the way until it gets to here, and it would be 1, right? So it would essentially just be 0, 1 in terms of a 2-bit string. And that's exactly what we want for the segment, right? We wanted those 2 bits to indicate which segment this instruction or this virtual address should be from. And so that's how we calculate the segment, right? This first line here. Now to get the offset, well, we apply this AND operator again with the virtual address and the offset mask. So you can see how both of these masks are basically just getting exactly what you want, right? The segmentation mask only has 1s for the first 2, so it's only going to get information regarding the first 2 bits in the virtual address. And the offset mask is basically 1s everywhere else, so it's only looking at information where after the first 2 bits in the virtual address. So these first 2 bits become 0 because of the zeros here. Doesn't matter what values were here. And then everything else is just 1 if it was 1, otherwise 0 if it was 0 for that. And that's how we get our offset. This information is then utilized in a couple like if statements to indicate or to detect whether there was an exception. So if our offset is greater than, say, some bounds value for that particular segment, obviously then it means that this virtual address does not exist within the segment, or it is not a valid address for this segment, and therefore you should raise an exception. If it is valid, so else, then we calculate our physical address as that base segment plus our offset. So the base value for the particular segment plus the offset. And then we can access some memory based on that physical address. So that's how you actually refer to or reference these segments. Okay, so just moving on or expanding upon this idea of referencing stack segments and virtual addresses within segments, there's additional information that our segment register can store. And that is whether or not our stack grows backwards or forwards. So before I've spoken about the heap, where the heap will grow downwards if you've seen those arrows, and the stack will grow upwards. So this is a case where the opposite occurs. And we need to check if our hardware supports this. So our segment register will have an additional field that indicates whether or not this segment grows in which direction. So if it's a 1, it will grow in a positive direction, so downwards in memory, or from lower addresses to higher addresses. And a 0 if it grows in a negative direction, so from higher addresses to lower addresses. And here you can see that in this grows positive field, basically. So it's 1 and 1, and then a 0 for the stack. So the heap, when the heap gets bigger, the heap will grow downwards, so it will eat up or get bigger downwards. The stack will get bigger upwards, so from this it will eat into this free space hypothetically. Now, just like we added this grows positive, there's an additional field that our segment register can contain, which allows for support for sharing. So a segment can be shared between address spaces, so between processes basically. And this idea of code sharing is still in use in systems today, but it requires extra hardware support. So again, you remember when we spoke about way back when we have multiple processes, multiple copies of the same process in running at the same time? Why do we need to store multiple copies of, say, that code part? Well, we don't, and that's because of the segmentation addressing and the sharing of segments. Now, extra hardware support is needed in the form of these protection bits, and this indicates whether or not a segment can be read or written to and executed on. So when you see read-write protection and stuff like that, that information is governed and stored in our segment register when we are processing information. So there's a few more bits per segment to indicate the permissions of read, write, and execute. Now, the last thing I want to talk about in terms of segmentation is that we looked at a coarse-grained approach to segmentation, where we only have segments for the code, heap, stack, etc., stuff like that, right? So a small number of segments. But there are systems today which utilize a more fine-grained segmentation approach, which allows for more flexibility for address space in some systems. And this was to support many segments. And because we have many more segments, well, we need hardware support that includes a segment table. Now, a segment table is basically just a huge or much larger segmentation or segment register. So in the fine-grained approach, we don't just segment for code, heap, and stack, but we segment for a lot more things. I don't want to get into the specifics, it's not super necessary, just that there are many more segments, and as a result we need a larger segmentation register, and that's called the segment table, and this still keeps track of bounds and base values, but for every segment. So the idea here, just a lot more segments. Okay, so moving on, I just want to speak a little bit about fragmentation, because this is going to help us segue into the second lecture, or the second part, which is free space management. Now, external fragmentation is basically little holes of free space in physical memory that make it difficult to allocate new segments. So say there is 24 kilobytes free, but not in one contiguous segment. So there's maybe 4 here, 6 there, 8 there, etc. Now, the operating system cannot satisfy the request for a 20 kilobyte sized segment, right? And that's because our memory space is so fragmented that there's no space for it. Now, the solution to this is compaction, and that is the rearranging of existing segments in physical memory. So compaction is costly. It requires stopping running processes and copying data to different locations, as well as changing segment register values. So it's moving of segments around in memory in order to make it a lot more, in order to have contiguous segments of free space. So this is what it would look like hypothetically. So say we have this as our physical memory representation. So there's some free locations, some allocated locations spread out. Now if we had to apply memory compaction, this would shift everything into allocated and free. So here we have now our allocated space between 64 and 192, and you can see that that would be the sum of all the allocated space here. And our free is basically everywhere else. So that was what memory compaction would do. And you can see it's shifting these segments around, and that obviously takes up quite a bit of resources and time. So this idea of free space management is what we're going to tackle in part 2. So thank you very much for listening.